talk about this course. This course is about automatic control. So basically, we got a plan. Since we're talking about single input, single output, you got a motor. What is the input of a motor? Voltage, right? You got a battery, so you put the input into your motor. You got an output, of course. Right? If this is a motor, and you say, okay, this is driving the wheel of the car, and you say you want to have the car to move like 50 centimeters, then stop there, then go back. What do you want? What is your goal? Your goal is your output is the same as your input, right? So it means that if I put my output over input, what do I need? What do I want to have? 1. Which means you got your output functions. Normally, when we are dealing with control system, we do Laplace transform. So when we have a Laplace transform, every variable is in terms of s. So I got my y of s. I got my r of s. This means reference. My y of s over r of s equals to 1. However, this is not possible because we are mechanical. The system we have is mechanical. When you have mechanical system, and let's say this is a motor. If you want to drive your motor with a frequency higher than 40 Hertz, it's not feasible because it's mechanical. It cannot go as fast as you want it. So anything beyond certain range, it will be restricted. So that's the reason we need to know how to push the frequency to an upper limit. And meanwhile, when we try to derive the relationship between output and input, we want it to be as close as possible. But sometimes we do have overshoot. Overshoot means that you guys have an experience. You turn on the knob, and you drive some kind of wheel. So when you turn on the knob and put this to the scale, it will. What it's going to do? Will this one rotate to the position you desire and step right there? Normally it won't. It will do something like rotating back and forth. That thing is something we call oscillation. And when it's oscillation, certainly you have some kind of overshoot. We hope that we do not have overshoot. Why? Because if this motor is used for surgery, and this surgery is using a knife, and this is open heart. Okay, so we say this one is going to move downwards, and the heart is over here. And you have overshoot. What happened? You kill the guy right away. In the States, the rest of the salary of the rest of your life is going to pay this patient. So normally we don't want to do that. So that's the reason we need to have good control theory. Goal is to make the output and input equals to 1. And we're going to talk about a lot of things behind this concept. We're going to talk about transient response, steady state response, how to make controller, and those kind of things. So basic output of this class is, first, we need to do modeling. That is going to be chapter 2. And when we do modeling, we need to know Laplace transform. Because when we are doing modeling, we are actually dealing with differential equations. We talk about acceleration, velocity, and position. Those things are in terms of time. So we need to convert everything from time domain into S domain. we do this, we are converting everything from the differential equation into algebra. Algebra is easier for us to process. Then we design our controller. Before that, we are going to do analysis of stability. We're going to talk about what is stable, what the definition of stable and unstable. When we say stable, what does that mean? When we say it's unstable, how it's going to look like? When we say it's critically stable, how it's going to affect your system or how it's going to affect the output, that is something we're going to discuss over here. Once we understand the stability of the mechanical system or anything, then we're going to design our controller. There are a few techniques we're going to talk about here. The first one is locus. We're going to talk about if we draw everything on S domain. That is essentially the fundamental part of control theory. This one, if you want to do PhD in the future in control theory, this part is something you definitely need to know, even though this is probably not the research focus nowadays, but if you go to industry, locus design is still popular. And second one, we're going to talk about PID control. PID control, you can just tune the coefficients of P, I, and D. We're going to talk about the effect of individual controllers. And after that, we're going to do pole placement. Pole placement is something easier. Basically, this is just algebra, which is easy to understand and easy to implement. And I think this is popular in most of the university teaching control theory. Like I know Purdue and Harvard, UCLA are using this method for their undergraduate course of control. But we're going to talk about those things in this class. Other than that, we're going to do frequency analysis using OB1. So over here, we're going to talk about what is your natural frequency. When you have a mechanical system like this, how is that going to see in frequency domain? When we see, most of you guys see I believe most of you guys watch the video, which is the Golden Bridge under the earthquake. The bridge is moving like hell. So what happened to that bridge? Can you do some kind of mathematical analysis to understand which part or which frequency is going to cause that kind of things? We're going to talk about that in this class. And if you really interested in that kind of phenomena, I would suggest you guys take vibration, because vibration will talk more intensive idea how natural frequency is going to look like. And if we have those kind of phenomena, can we compensate that using another component so the natural frequency is going to be changed so that it's not going to be damaged when we have those kind of disaster. And after that, we're going to talk about my quiz. This is the basic of digital control. No, we're not going to cover digital control in this class, but if you want to do that in the future as a graduate study, it's something you might need to understand. And after that, we're going to do controller design. Frequency domain. This one over here is the concept. So we're going to talk about the next controller. I think all those things is going to take us for the whole semester. So if we still have time, we're going to talk about state space. Okay. State space is essentially matrix representation. It's not difficult. It's just another way to represent the model. This one over here is easier for us to make everything stable, and sometimes it makes more sense to everybody. But if you are new and not so familiar with linear algebra, then we're not going to cover this part. There's a reason. Most of the material is up to here. Okay, but if you want to do more things like this, you can take linear system. I think Dr. Du is teaching that course right now, but it's I think it's 600 level, should be graduate level. So maybe after this class, you might want to take a look at that course. Okay, so let's talk about one of the since most of you guys do not have your notes available with you, how many of you guys have your notes? Okay, not everybody. So this time I'm going to write down the problem statement. Next time, please print out the notes so that you know what I'm going to do, and I don't need to waste my time writing down those kind of things, and you don't need to guess what I'm writing over here. Okay? Consider this. The object. Precisely. Okay. Over. It's what? Open loop. And close loop. Close loop. Such system. So this one over here, if you take a part of your hard drive, what are you going to find? Of course, most of you guys is only interested for the magnet, always strong. You can stick it that everywhere you want to. But over here, they have a stack, and they have voice coil over here. This is a coil. We can treat this one as a motor. So you got the controller somewhere. You got circuit. And you write a code for the firmware over here. There is a microprocessor in your hard drive and control the position that located this one. This one over here has 2 parts. One is a piezo material over here, so it will fine-tune the position of the reading head. And the other one over here is a voice coil, so you can actually rotate this one in a larger range. So combine those two things together, we can control the reading head anywhere we want to on the disk. So when we are talking about those kind of things, there are 2 types of controllers we actually want to deal with. The first one is open loop. The other one is closed loop. They have different definitions. So we're going to talk about this after 10 minutes because I think I need to give you guys. Basically, this example is simply talk about the concept of open loop and closed loop. So let's first talk about So when you try to control a car, for instance, you want to control a remote car, what can you do? You can just turn on the power and set the voltage to 5 volts. The car certainly going to move forward, right? But you have no control where it's going to stop. So you need to have some kind of feedback. When you are driving the car, what is the feedback? Yourself, because you're looking at the car. You know where the car is located. So you're going to tune the voltage to be higher, smaller, or set to 0, make it stop. So essentially, you are the feedback, you are the sensor, and you are also the controller to control the position or the velocity of the car. So, but you can certainly say, okay, I don't care. I just want to turn it on for 5 seconds, then it stops. It's certainly going to stop. So I don't care where it's going to be located. That is open loop. So when you are doing your control, there are 2 types of control. You got 2 options. One, open loop. This is without feedback. The second option is closed loop control. This time, the difference between open loop and closed loop is whether we have sensors and whether we have control feedback. So this one certainly we're going to have feedback. Okay. So if you have download your notes, the figure I'm going to draw is actually over here. So let's talk about open loop. Just like what I said earlier, you've got your motor. Let's say the function of your motor is GP. This one over here, and this one, since we're talking about hard drive, the output of your hard drive, the output of this reading head is certainly the position. So we are going to have right? And this is a motor. When you want to drive a motor, how can you drive a motor? You use what? Voltage. So over here, the input for this one is going to be used. Okay. So this is a motor, this is a voltage, but nothing. This doesn't have any information of position. So in order to have your head to be located at a specific location, you need to have a controller. Okay, so this one over here is going to generate control command, which is voltage. That is going to send to your motor. But before you send it to the controller, before you send a signal to your motor, you will need to have what do you want the head to be moved. So this one over here is desired checking position. Okay, so this is going to be complete my system. But you might notice that I don't have any sensor. So when this one says it's going to be located at this sector, we need to trust it because we have no way to check whether the system is actually at the location unless you have a sensor. But in this case, since we say it's open loop, it means that we do not have any feedback. Okay. There are 2 specific terms over here you guys want to remember. this one and this one, they are called transfer function. Okay. In chapter 3, we're going to talk about transfer functions. That is basically from Laplace transform. So again, if you guys forgot how to deal with Laplace transform, it might be a good idea to review that before we talk about chapter 3, topic 3. Okay. So second one, over here. Let's do it. Output. This is my ideal case. Right? So in order to do this, earlier we talked about ys equals ys, the relationship between ys and rs, right? It means that in order to make this one equals to this one, gc multiplied by gp must equals to 1, right? Because if this one multiplied by 1, then it's going to be your output, which means your output is going to be identical to your input. Does it make sense? So if that is a goal, we hope this one as close to 1 as possible. Sometimes it's not possible, but if we can get everything close to 1, that will be great. It means that the actual output position should be equal to the desired path. Okay, so GP is the model of this guy. We can represent everything in mathematical equation, right? So when you try to design a controller, keep in mind we want to design a controller which makes GP plus multiplied by GC equals to 1. So how can you obtain the transfer function of GC? Simple. GC equals to 1 over GP, right? So if we can identify what is my transfer function of the plane, the controller can be designed just taking the inverse of the transfer function, right? Okay, the end of this class, you guys can go because this is simple. Though this is the idea, but we cannot do that because if you do something like this, I can tell you 95% of the case, the system is going to be failed or be unstable. There are a lot of restrictions like mathematical or physical restrictions prevent you from doing this. So we're going to talk about control theories. That is going to compensate for this one. That's a reason. That's also the reason open loop controller is not popular. Only when you try to do something in a quick response, then we use open loop control. Otherwise, we will prefer to do closed loop control. So essentially, they are the same. This is my controller. This is my motor. This is my actual head position. Okay, so this one is the same as my open loop control, but I'm talking about feedback control or closed loop. which means I'm going to take my position of the reading pen. Go through a sensor and put it back. This time, this one over here is my desired tracking position. Okay, this time this is my desired trajectory. Goes into a system, but this this number over here needs to be compared with what is my current position. So we put plus and minus. So your desired minus your actual position. The output becomes your error. So this one is your error signal. How much difference between my actual output and my desired input? That is your error signal. All for the rest of the semester, we are analyze the error signal because we try to get error equals to what? 0. Because when error equals to 0, it means that your output is the same as your input. Does it make sense? So this part over here. We can simplify this with one simple G. Okay? And the rest of the part, I'm going to write it down. It's nothing to do with something we talk about now because we're going to go through this part in chapter 3. So my output Y and my input R is going to be G over 1 over GH. This one over here is blank. Multiplied by controller. This one is, and this one is sensor. So when we are doing something like this, Y over R needs to be equals to 1, right? Because when we say it's 1, it means that the output is the same as your input. So over here, how can we make it happen? If your edge is a very expensive one, the output is the same as, the reading is the same as your input. So we can just ignore this part and make this one as 1. The next thing, if you want to make this part equals to 1, you need to make G close extremely large. So the 1 compared to G is kind of small. When this one is small, we can approximate this part equals to 1. That is something we call eigen system. We're going to talk about this in chapter 5 in your textbook. Not now. And this is going to be something related to controller design. Okay? This part over here is going to be chapter 3. Talk about block diagram. Okay? Any questions so far? Am I going too fast? Or this is okay?